This command allows you to take std_in text, source it with a key, and output to std_out. This allows you to encrypt or decrypt text using the one-time path algorithm. This algorithm is proved to be quantum proof when you use a key that is totally random, is never reused between messages, and is shared across the parties using a secure channel. Once the initial key has been shared through a secure channel between the parties, it's going to be consumed on every time the message gets sent. So the first message will consume the first part of the key, and the parties will remove that part of the key. That way the key is never reused between messages. In this video I'm going to go through this process, explain you the steps and the internals of the command. Alice wants to send a message to Bob. In this case I'm going to use the simple example with the letter A, which is going to be the message to be sent. The message has to follow through this unsecured channel till the destination, where Bob receives it and produces the same text using the same pattern. So this is the one-time path algorithm. Alice in one side, before sending the message, will take the plain text, sort it with a key, and this will produce the cipher text. The cipher text is going to travel through this unsecured channel, which is going to be received in the other side by Bob. Bob will do the same thing. We'll take the cipher, source it with the key, and get the plain text. This is the one-time path algorithm. I'm going to show you how the SOR procedure works. SOR internally in your chip is a logic gate. It means exclusive OR. And this is the truth table on the left. This is the table that you have to look in order to calculate the output for two parameters. In this case I'm going to use the letter A as before. So A in ASCII is the 01100001 in binary. So let's take the plain text in binary, which is on top. And this is the key that both Alice and Bob have. So 0 with 0 is 0, 1 with 0 is 1, 1 with 1 is 0, 0 with 0 is 0, 0 with 1 is 1, 0 with 1 is 1, 0 with 0 is 0, 1 with 1 is 0. So this will be our cipher text after applying the SOR algorithm. So if this key here is random and both have it, then this is considered a quantum proof algorithm, because the message, which is the secret, right, it switch with a random key. This key is random, so every time you use it, you don't reuse it again, you only use it for this message. And because this switch on the text is random, you randomly switch the value. There is no way you can, from the cipher that someone might capture, produce the plain text without knowing the key. Okay, so this is how the keys look in time after the message gets sent and received. So the first time, one of the parties will generate a random key. You can do this with dices or with the computer, whatever. The key here is that this number has to be a random, truly random number. And then this party, let's say that Alice generated this key, shares it with Bob through like a secure channel. So both parties have this key. Let's say that Alice sends the letter A. So the letter A will consume this amount of characters from the key. So this key gets used for encrypting the letter A and is never reused again. So Alice had this entire key, and after sending the letter A, it lost this part of the key, but it still have the remaining part of the key. So this is the new key. because the next message, she will start using this part, not the first part. And that's how the key never gets reused. So the message gets received by Bob, and he has the original key because he hasn't used it to decrypt or encrypt anything. So in this case, Bob will consume also the same part of the key to decrypt it. So he is going to make the switch with the plain and the key, and is going to produce the same A plain text. So now Bob has received the plain text, and both parties have a new key which is identical, which is this part. So this is what this command does. It uses this part of the key to encrypt or decrypt text, and it produces and saves this new key. So this new key gets saved also for Bob. In this video I'm going to show you how to use the command. So you first go to the OTP GitHub page under tags. Let's just use the first version. So I copy this link. First I download the release using the wget command. I have the file there. Let's unzip it. First build the command and test it. It's built and it's tested. So the command is working, and it's output in the bin folder, the binary. So let's install it system-wide. And now I can use the OTP command. So first thing, I'm going to generate a key file. In this case, I'm not going to put a random content in there, but just some random, semi-random characters. And I'm going to have a plain text with the text hello world. So I have those two files there. Those two files. So this is the random key that both parties need to have, and this is the message that you want to send. So I'm going to say cat or echo cat plain OTP with a key, and this will put in the screen the cipher text, but I'm going to output to a file called cipher txt, or even better, the same as this, but to print it both to the screen and to the file, the T command. So it outputs this, but it's not readable because it didn't produce an ASCII after doing the SOR. You can see the cipher file that contains binary basically. So I have these three files now. I have these three txt files. So this is the encrypted version of the plain using this key and the one-time path cipher with the OTP command. I'm going to do the opposite. I'm going to decrypt it. So I'm going to say cat cipher and then OTP. But first, before I do that, you might notice that it created a new text file. So this is the part that the alias that one side will do to encrypt the text. It encrypted the plain text using the key, and because this key part that was used cannot be reused, it created another key file which contains the remaining part of this file that hasn't been used. So let's create a folder called alias, because in this case I'm going to do both parties, encryption and decryption, in the same folder, but I'm going to move the key, this key, which is the next key for Alice, because she has sent the message already, so she consumed this part of the key, so she got a new key file. I'm going to put it in a folder called Alice, and now Bob will say, okay, Bob will also receive the cipher text, so it's going to say cat cipher OTP with a key, because he still has the original key, because he hasn't received anything yet. It's the first time he is going to use that key. I'm going to say output this to original or plain after the encryption. So if I compare, as you can see, it also generates an X key. So I'm going to say make dear Bob move this key to the Bob folder. This is just for the example. So both the plain and the plain after encryption should be the same, and they are. And also the next key of Bob, this is the next key of Bob, should be the same as the next key of Alice. And it is. So as you can see, it's producing the ciphers and the next key files.